The following program is part of Cable in the Classroom, a service of the cable television industry and your local cable company.
You're not going to need this for the next 30 minutes.
The second law of thermodynamics?
What was the first law?
I don't know. Hey, welcome to SportsFigures,
On ESPN 2,
where sports and science go one-on-one,
where physics get physical,
where math gets mathematical.
where sports figure.
Go figure.
It's SportsFigures.
I'm standing here with bungee jumper Doug Anderson as he prepares for his final jump in today's X Games competition. So Doug, tell us what it is you're doing here to prepare for this big jump.
I'm getting my energies balanced.
So you're getting in touch with your psychic energy?
No, the energy's right here in the cord.
Wow, energy in a bungee cord. So this must be some kind of new age spiritual thing then.
Nope, it's strictly physics.
Wow, physics. So you're getting in touch with the physical universe and stuff.
Yeah, like physics.
Yeah, well, this is just a physics book.
Bungee jumping's all about physics. You know, potential energy and kinetic energy. Balanced energy is what makes sure I don't hit the ground. That's why I have to measure this bungee cord before I jump. So if you don't mind.
Oh, yeah, sure, man, sure, I can dig it. Well, you heard it here first. There's all sorts of weird energies involved in not hitting the ground when you bungee jump.
Hey, did you know that the very first bungee jumper was a woman?
Running away from a man.
Bungee jumping comes from a tradition in the Pentecost Islands in the South Pacific. Today, bungee jumpers want as much stretch out of the cord as possible to get the highest rebounds.
But how do they figure out how long the cord should be to snap them back just before they hit bottom?
Well, let's join SportsFigures Kevin Flynn at ESPN2's X Games with 1995 gold medalist and 96 silver medalist Doug Anderson to leap into some answers.
Whoa! That was close. So what could be more important to a bungee jumper than how long his cord is? Because if his cord is too long, well... So how does a bungee jumper figure out exactly how long his cord should be? Figuring out how long a bungee cord should be is really just a matter of energy balance. Energy just means the ability for something to do work. If something does work, it loses energy. The amount of energy it loses is equal to the amount of work it does.
Kevin, I'm beat. Can I stop now?
Sure, take 5. Good kid. Now there's 2 types of energy. One is potential energy, and the other is kinetic energy. You can understand it this way. This battery is potential energy. There's energy in here, it just isn't doing anything. Kinetic energy is when something's moving. You see, the potential energy of the battery is passed to the kinetic energy of the fan, which passes kinetic energy to the air. See, this tells us something very important about energy, that it can be passed from one thing to another. Right now, the motor in this elevator is doing work. It's lifting me up. But it's also giving me energy. How does it do that? This elevator has given me potential gravitational energy. Whoa, and I can feel it all over. It's also given me the potential to fall off. If I did that, I would start to move down because of gravity. My gravitational potential energy would be converted into kinetic energy. My first second, I'd be falling at 32 feet per second. My next second, I'd be falling at 64 feet per second. And by my 5th second, I'd be falling at 160 feet per second. That acceleration is due to gravity. And that's a lot of kinetic energy. This tower has given me all kinds of potential energy. And I feel better already. Right now, Doug, you are full of potential energy.
Oh, yeah? I thought it was an adrenaline rush.
Well, to find out how much potential energy, we need to use a little equation, and that looks like this.
Awesome.
It's really quite simple. The PE stands for potential energy. M is the mass of the jumper. How much Doug weighs? 150 pounds. The G is the acceleration of gravity, 32 feet per second squared. And the H is the height, or how far Doug's going to fall. The tower's 160 feet, so we want Doug to stop before that. Let's say 152 feet. A little quick math, and we get 729,600 feet squared pounds divided by seconds squared. That's your potential energy.
Oh, yeah? What's all that feet squared stuff?
It's just another way of expressing energy. But what's important is this number here.
Okay. Should I jump now?
No, first we have to balance out your potential energy. Otherwise, you're gonna go splat.
Oh.
Hey, come on, you guys, let's show some kinetic energy. Let's go. All right, that's better. All right, now what happens when that guy jumps from the tower?
He's gonna fall. So the potential energy is going to be converted to kinetic energy.
Right and right. But how come he's not gonna hit the water?
The bungee cord.
The bungee cord, that's right. The bungee cord acts as a spring. So we have to learn how a spring works. And for that, we need the letter K. We use K to represent the spring constant, the amount of force it takes to distort an object. An object that's really easy to distort has a low K value. An object that's really hard to distort, has a high K value. The thing about the spring constant is that it gets multiplied by how far we stretch the material. X, K, times X, X. The further I stretch the material, X, the more it wants to pull back, depending upon what its K is. So to test the K of a material, we have to see how much force it would take to stretch it 1 foot. All right, Seth, you're stretching the cord about 1 foot. How much force are you putting on the cord?
112 pounds.
Since Seth pulls the cord 1 foot with a force of 112 pounds, the cord has a K of 112. When we stretch a bungee cord, we're performing work on it using kinetic energy. Now remember we said how energy can be transferred. The kinetic energy of stretching the cord is transferred inside the cord to potential energy. The amount depends upon its K. And that is the secret to bungee jumping. It's called the law of conservation of energy. That means that energy can't be created or destroyed, but it can be converted from one form to another.
Hey, somebody! Anybody?
When Doug jumps, his potential energy is converted to kinetic energy. He's moving. The cord begins to stretch, and as it stretches, potential energy builds inside the cord. If we want Doug to fall only 152 feet, we have to subtract the unstretched length of bungee cord, because X equals the amount the cord stretches. So we get the bungee's potential energy equals 1/2 112 pounds over second squared times 152 minus L squared feet squared. The 1/2 averages out the change in force over the distance the jumper falls. And L is what we're trying to find out, how long the bungee cord should be before it's stretched out. We balance that out with your gravitational potential energy standing here, with the bungee cord's potential energy when it's stretched out. When the two equal out, you stop going down.
And in the process of sucking up all that kinetic energy, the bungee gets stretched to the point where its force is far greater than the force of gravity. So I rebound.
Let's crunch some numbers. We end up with an equation that looks like this. 729,600 equals 1/2 times 112 times 152 minus L squared. The gravitational potential energy equals the bungee potential energy. The only number missing is L, how long the cord is. After a little quick math, we get... Math takes a little kinetic energy. After a little quick math, we get 37.85 feet. That's how long we want our bungee cord to be. Okay, Doug, you have a bungee cord that's 37.85 feet. You have the potential energy to pull you back at 152 feet, and the tower is 160 feet. So you should be all set.
Can I jump now?
Now you can jump.
All right.
The gravitational potential energy is being converted to kinetic energy. The cord stretches until it has absorbed all the kinetic energy back into potential energy. When that happens, Doug stops and springs back.
All because of the balance of energy.
Hey, somebody! Anybody?
Hi, I'm Chris Allen. I'm from Wellington, New Zealand. I'm the bungee coordinator here in association with the North American Bungee Association. This is one of the competition bungees that we're using at the Extreme Games, and you can see there's just multiple numbers of strands of rubber. We use 5 different bungees for the competition, so regardless of the jumper's weight, they all get the same extension, they all pull the same G's of gravity, and they all get the same rebound, and everyone's on a level playing field. It's all math, it's all physics, it's you know, it's all to do with the stretch, the amount of rubber you're using, the distance you're traveling, the speed you're traveling at. There's quite a few equations to take into account.
So with a little bit of physics, we can bungee jump perfectly safely. You know what? I think I just don't have the energy for this today.
Hey! Anybody? Hey, somebody!
Thanks, Kevin.
And thanks Doug Anderson, Chris Allen, the students, and the folks at ESPN2's X Games for helping us out on SportsFigures.
An object at rest will remain at rest until something makes it move. An object in motion will remain in motion till something stops that groove. You see, force equals mass times acceleration. Force equals mass times acceleration. Force equals mass times acceleration, and that is Newton's rule.
Hi, I'm Mike Richter of the New York Rangers. You're watching SportsFigures.
The crowd goes crazy!
The preceding program is part of Cable in the Classroom, a service of the cable television industry and your local cable company.